Hello out there, and good morning, afternoon, or evening. My name is Brian Cabana. This presentation is something I'd like to call a closer look at the fundamental theorem of calculus. So the objective here is to give an intuitive account of how and why the fundamental theorem of calculus works. Note that this is not a formal or rigorous proof. Again, the purpose is just to get a picture in our minds as to what the fundamental theorem of calculus actually says and does. Now, there are many resources we can turn to for rigorous proofs, from textbooks to other videos, which I might link to, but none of them, to my mind, adequately convey an intuitive notion as to what's actually going on with the theorem. So hopefully this presentation can fill that space in the market. Just note quickly that you're probably going to need some background in calculus for this video to make any sense. You'll probably need to know what a derivative is, what an integral is, what it means when I say the slope of the tangent. I'm going to walk you through some of the concepts, of course, but you might not understand what's going on if you don't have at least some background in calculus. All right, so let's begin by stating the fundamental theorem of calculus. All right, so let's say we have this function, y equals f of x, right? This function is shown here in this bright blue curve here, right? And let's say we have another function, y equals big f of x, which is depicted here in this red curve, right? So the fundamental theorem of calculus holds that if over a given interval, in this case delta x, and the red delta x is the same as the blue delta x. So if over a given interval, our little f of x is the derivative of big f of x. So if this little blue curve y equals f of x here is the derivative of the big red y equals big f of x here, then the area under the derivative curve, right, so this area in this blue region, will equal the vertical displacement, that's right here, right, the vertical displacement, the change in y, of the parent curve, or the anti-derivative curve. So to sum it up, if little blue f of x is the derivative of big red f of x, then the vertical displacement of the curve y equals big red f of x, this delta y, will equal the area here in dark blue underneath the curve of the derivative, y equals little blue f of x. So that's the fundamental theorem of calculus, and hopefully that was review. The real purpose of this presentation is going to be to answer a simple, but to me, very subtle question. It's a question about information. It goes like this. I know the displacement of the red curve easily, only through knowing two numbers. So to get the change in y, all I need to know is the position of the curve at the beginning of the interval. In this case, it's 0 because it's on the x-axis, and the position of the curve at the end of the interval, right? So if I know the value of the curve at the beginning and the value of the curve at the end of the interval, I can get my delta y. But how is that enough information to determine the area under the curve of the derivative function? It seems astonishing that those two numbers have enough information packed in them to determine something like the area underneath the curve on the bottom. So to answer that question, I'm going to review a little bit about what it means to say that this curve here, y equals little blue f of x, represents the derivative of this curve here, y equals big red f of x, right? So what does it mean to say that the curve on the bottom here is the derivative of the function on the top? Well, this is what it means, right? So at any given point, let's say x1 here, right? The derivative of the big red curve is simply the slope of the tangent at that point. So in this case, right, at this point, this delta y over delta x will be 0.75, right? So if the curve on the bottom is the derivative of the curve on top, it simply means that the value of the function on the bottom at that point also has to be 0.75. So I'll say it again. If the curve on the bottom maps the derivative of the function on the top, then at any given point, in this case x1, the slope of the tangent of the parent curve, in this case 0.75, right, will be the same as the value at that very same point, x1, of the curve on the bottom, 0.75. And there's nothing special about 0.75. At any point, the slope of the tangent at the curve on the top is going to be the same as the actual value, the y value, of the curve on the bottom. Now this is important, so if you have to play this slide again or rewind at this point, now would be a good place to do so because we're going to keep moving. All right, so hopefully you have this information under your belt. So we're going to simplify a little bit. So up here you have the old distance, velocity, time fact triangle from like algebra 1. Remember that? Distance equals velocity times time, velocity equals distance over time, etc. Right? So I'm shifting from x and y to distance, time, and velocity because it should present, I think, a more relatable context for what I'm about to say. All right? So notice that this graph maps distance over time, right? So this is mapping distance over time. And if that's the case, then the slope of the graph is simply going to be the velocity. It's going to be the change in distance over the change in time. Nothing new about this. You should hopefully have had this under your belt since Algebra 1. Nonetheless, I do want to set up an example because we'll be referring to this example for a while. In fact, for the duration of the presentation, I'll be consistently going back to this exact example. So again, we have our fact triangle, distance equals velocity times time, velocity equals distance divided by time, and though we won't use this too much, time equals distance divided by velocity. So if our skater travels 90 feet in 10 seconds, well then we just divide distance by time, and it gives us the velocity of 9 feet per second. Now this is nothing groundbreaking, right? This is stuff that we had in, first year of algebra. But here it hopefully gets more interesting. So we've split the graph, and we see that the top graph here maps distance, and the bottom graph maps velocity against time. So we got distance over time and velocity against time. And note that velocity mapped over time is the derivative of distance mapped over time. So what does that mean? It means that if I'm graphing distance against time, like on the curve at the top, or in this case the function, the straight line, then the slope of the line is going to be the same as the value of the velocity function. And note here that because distance equals velocity times time, something interesting happens, right? So when we're mapping distance against time, the change in distance is simply going to be the vertical displacement of the function. But when we're mapping velocity against time, right, the distance is going to be velocity times time, which is the area of the rectangle. So we already have a connection between this vertical displacement of the distance function right here and the area underneath the velocity function. Again, this is important. So if you didn't quite understand that, please go back and review this slide. It's a crucial step in the argument. So you'll notice that the function on the top is simply a straight line with a constant slope. And accordingly, the derivative of that function on the top, which is the velocity function on the bottom, is a constant function, a simple horizontal line. So in this next example, we're going to change that up. So you'll notice now that we no longer have a constant velocity for our skater, but rather he travels his 90 feet by first going a bit slowly for 5 seconds, 6 feet per second here, and then traveling a little faster at 12 feet per second here, right? Of course, he's still traveling for 10 seconds total, and he's still going up these 90 feet in those 10 seconds, so his average velocity is still 9 feet per second. And here are some calculations with which we will verify this. So your total distance has to equal the distance in the first section traveled plus the distance in the second section traveled. So these 90 feet have to equal the distance traveled when you were going at the relatively slow velocity of 6 feet per second, plus the distance traveled when you were going at the faster velocity at 12 feet per second. You changed your velocity, but your total displacement and hence your average velocity remain the same. Again, nothing groundbreaking. More is revealed, though, when we split the graph again. So on the graph on top, the distance function, we have this relatively narrow velocity of 6 feet per second. We go down to the velocity curve and see that it matches this segment here of 6 feet per second, plotting velocity against time, little horizontal line segment. We see here that this much steeper sloping line, when the skater is traveling at 12 feet per second, corresponds on the velocity chart to 12 feet per second. See the horizontal line segment here. And again, that must correspond to this displacement, right? When you multiply those 12 feet per second with the 5 seconds, you get this displacement, the one, the purple, right? That's the purple displacement under the 12 feet per second function. So that means that if I add this purple rectangle underneath the section of the function where v equals 6, when the skater's velocity was 6 feet per second, with this area, on the area of this purple rectangle, where v equals 12, well, that's just that first distance plus the second distance. And that has to equal the total displacement of the distance function. It simply has to equal those 90 feet that our skater traveled. So to recap, distance equals velocity times time. Velocity times time happens to be the area of this purple rectangle underneath the velocity function. All right? That thus has to equal this distance. This rectangle, the area under this rectangle, also equals velocity times time of the section of the function where v, velocity, equals 12, and that has to equal this displacement. So when I add both of these rectangles together, I have to get the total displacement. So I hope you guys are beginning to see where I'm going with this, because the same thing holds when I have three subintervals of velocity. So we have the displacement of section 1, the displacement of section 2, and the displacement of section 3. And all of these velocities, right, under these subsections are becoming increasingly steep, which means that the rectangle, if we're plotting velocity against time, have to be increasingly high. Or rather, the value of the velocity function is increasing. But regardless, the area of each of these rectangles still has to equal the total displacement. And it doesn't matter if they're 3 rectangles, 5 rectangles, or 7, as long as the average velocity remains 9 feet per second. And notice that this average velocity here is marked by this light blue rectangle in the background. That's just 9 feet per second times 10 feet. So that represents here, see that, the blue line up on top. Here's where I should point out that the velocity function has to be the derivative of the distance function, so long as we're talking about the same function, right? So as long as this distance function is the parent function, the velocity function is its derivative, which means that the value of this, well, line here has to equal the slope of this line at v1. The value of the velocity function here has to equal the slope at v2. And the value of the velocity function here equals this steep slope here at v3. So look at the math on the bottom and we find that nothing's really changed, right? Since the area of these rectangles represent velocity times time for the subintervals, we find that velocity 1 times time 1 plus velocity 2 times time 2 plus velocity 3 times time 3 has to equal the average velocity times the total time, thus has to equal the total distance traveled. And we find that if we expand the number of rectangles indefinitely, nothing changes, because the area of each rectangle simply represents the velocity of a subinterval times the time of a subinterval, and that it all represents a portion of the total distance traveled. And the sum of all these areas simply represent the sum of all of these distances. So your distance, measured in your distance function, will also give you the sum of all these areas of all of these rectangles underneath the velocity curve. Here, the number of rectangles has expanded more or less to infinity. We no longer have rectangles, just an area under a velocity curve. But the velocity still represents the derivative of the distance function. Thus, this distance traveled, because of the reasons we've gone through extensively in earlier slides, will have to give you this area, this collection of V1, T1, V2, T2, all the way to infinity, as the number of rectangles expands without limit. And that brings us right back to where we started from, hopefully knowing a little more, or at least a bit more intuitively, than what we knew before. And nothing changes when we replace the d's and v's with y's and x. Because if this little blue y equals f of x, right, if little blue f of x is the derivative function of big red f of x, right, as it states here, then the area under the derivative function, all this guy, will have to equal the displacement of the parent function, or the antiderivative function, as it states here. And that pretty much concludes our discussion. Our pointer did a great job today. Hey, very good, pointer. Nice work. All right, thank you. That'll do, pig. That'll do. All right, that's about it. Assuming anyone's still with me, which might be a charitable assumption, thank you very much. I hope you learned something today. On behalf of the group and ourselves, I hope we pass the audition. And I mean that in more ways than one. So this is my thank you parting statement. I'll end with the conclusion of a formal statement of the fundamental theorem of calculus. You notice that there are continuous intervals and all that business there. We covered it, but we didn't actually give you the formal statement in black and white, clear as crystal like we have there. And also we should know that that's the second part of the fundamental theorem of calculus. The first part gives you a related but obviously not identical facet of this rather ingenious discovery of Leibniz and Newton. All right, thanks a lot.